Okay, dear students, today I will discuss the numerical problems on this chapter wave optics. So, theory part of this chapter has been completed for this academic year. Okay, so the first problem on Young's double slit experiment. So, here in this chapter, most of the times in annual exam and in midterm exams, they have asked numerical problems on Young's double slit experiment. Related to fringe width or the finding wavelength of the light used in the experiment, or in case of shifting the screen away or towards the plane of slits. Such problems have been asked. So firstly, the problem number 1. In Young's double slit experiment, the slits are 0.6 millimeter apart and are illuminated by light of wavelength 500 nanometer. The screen is placed at a distance of 1.2 meter away from the plane of slits. Calculate the distance of fifth dark fringe and second part, eighth bright fringe from the midpoint of the fringe pattern. So this is the question. Okay, let us see what numbers are given. Firstly, slits are 0.6 millimeter apart, means slit separation. So in the first problem, given data, given data, slit separation, the standard symbol in the derivation of fringe width expression, we have seen small d, slit separation. It is given 0.6 millimeter, but you cannot take this number only, you have to convert in SI system. Millimeter is given, so milli is a prefix, milli means 10 power minus 3, so substitute that. 0.6 into 10 power minus 3 meter. The next number given, wavelength of the light used in the experiment 500 nanometer. So wavelength, so first rightly the data given, wavelength lambda equal to 500 nanometer. Usually wavelength either they give in nanometer or in angstrom. They don't give in 10 power, very rarely they may give nanometer or angstrom. So in case of nanometer, if the wavelength is given in nanometer, nano means 10 power minus 9. So what you have to write is 500 into 10 power minus 9 meter. You can simplify this 500 as 5 into 10 power 2 is there, 10 power minus 9 is there, so 10 power minus 7. Okay, so meter, this much. The next number, the screen is placed at a distance of 1.2 meter away from the plane of slits. So distance of screen from the slit section, it is from the slits or plane of slits is capital D. That number is how much? 1.2 meter. 1.2 meter. This is the distance of the screen. So let us see the experimental setup. Actually not required for solving the problem. Let me tell you. So this is the plane of slits and this is the screen, and the midpoint of the screen will come here. This is the center of the fringe pattern. Okay, so this is the screen and here is the plane of slits. And light illuminated on the screen, illuminated on the slits here of wavelength 500. Actually it is derived from a single slit S. Okay, these slits are S1 and S2, and light of wavelength used of 500 nanometer. This is the setup. Now here central bright fringe is formed. Remember how the central bright fringe formed on the screen? This is the central bright fringe at the midpoint of the screen. Okay, then the first bright fringe, distance of first bright fringe on the screen it is. I will turn the screen like this, I will show you. Okay, like this it is the setup, the fringe pattern. So first bright fringe, then second bright fringe, third bright fringe, like this it continues on the screen. Okay, third bright fringe. So first bright, second bright, third bright, like this. and after a central bright fringe, this is zeroth bright fringe, okay, central bright fringe, okay, bright fringe, okay. Now this distance, first fringe is beta, and this first bright fringe to second bright fringe also beta. Definition of fringe width is distance between successive bright fringes or distance between successive dark fringes, okay. Successive dark fringes means, see, this is the midpoint of the bright fringe, dark fringe, this is the midpoint of the another dark fringe, so this is also beta only, fringe width, okay. The midpoint of the screen, I will take it as O here, midpoint of the screen, that is center of the center bright fringe is O, and first dark fringe is this first dark, and this is second dark, no light. So first dark to second dark distance is beta. Central bright to first bright is also fringe width beta. First bright to second bright fringe also beta. So like this is the situation. And now fifth dark fringe from the midpoint of the fringe pattern. So for this there is a formula. Okay, so there is a direct formula for the distance of dark fringe. Distance of dark fringe from the central bright fringe. Okay, so first calculation what we need to do is distance of fifth dark fringe. Okay, generally I write distance of nth dark fringe from central maximum, from central bright fringe. Central bright fringe. The formula for this is xn equal to n plus half lambda into d divided by small d. So n plus half lambda d by d. Question is fifth dark fringe. So for fifth dark fringe, what is important? Fifth dark fringe. Okay, n value is 4. 1 less. Dark fringe, you have to take n value 1 less than the which particular dark fringe they ask. If it is a 10th dark fringe, n value you have to take 9, 1 less. So here x5 is substituting n value 4 for fifth dark fringe. So 4 plus half lambda d by d. Lambda 5 into 10 power minus 7. So 5 into 10 power minus 7 into the capital D value. Distance of the screen I have taken here 1.2 meter as given in the question. Okay, sometimes they may give that number in centimeter. Then divided by small d value, distance between the slits, 0.6 mm. Okay, 0.6 mm. 0.6 into 10 power minus 3 millimeter. 10 power minus 3 meter. It is millimeter, so 10 power minus 3 have to multiply. Now cancellation you see. 4 plus half, that can write 4.5. Half is 0.5. 4 plus 0.5, 4.5. Okay, into 5. Then, okay, cancellation you can see here. The 1.2 2 times and this 0.6 1 time. Okay, so 1.2 by 0.6 is 2. If you want, you can use calculator. 1.2 by 0.6 is 12 by 6 is 2. Okay, so that is 2. Then power of 10, here minus 7 is there, here minus 3 is there. So it is 10 power minus 4. Okay, so 10 power minus 7 and denominator 10 power minus 3. So that is 10 power minus 4. Now you see 2 into 5, 10. Okay, 10 into 4.5. Okay, or okay, I can write 4.5 into 5 to 10. 10 into 10 power minus 4. Okay, 10 into 10 power minus 4. This number is 10. Okay, so 10 into 10 power minus 4 is 10 power minus 3 meter. Okay, 10 power minus 3 meter unit. So this is the required number for this first part. So the answer is 4.5 into 10 power minus 3 meter, or we can also write 4.5 millimeter. Not compulsory, but you can write. You can write as shortly 4.5 mm. Okay, so 4.5 into ratio minus 3 meter is okay, fine. Next, second calculation, 8th dark fringe from the midpoint of the fringe pattern. 8th dark fringe distance. You want to find out distance here. So distance of 8th bright fringe from midpoint of the fringe pattern, that is center of the fringe pattern. So for that the formula is distance of bright fringe, distance of nth bright fringe, nth bright fringe, nth bright fringe from center of the screen, from center of the screen or center of the fringe pattern. Okay, so that formula is xn equal to n lambda d by d. Okay, so here we need a distance of 8th dark fringe, so x8 is required, 8. So 8 into lambda wavelength. Okay, lambda is the wavelength, so that is 5 into 10 to the minus 7 into 1.2 capital D value, 1.2 meter, then divided by small d, slit separation 0.6 millimeter. Okay, 0.6 into 10 power minus 3. So simplifying like previous. So 1.2 by 0.6, direct calculation you can do 1 this 2 times. Okay, so 2 into 5 10, then 8 into 10 into 10 power minus 4, 10 power minus 7, denominator 10 power minus 3. So 10 power minus 3 take numerator, it becomes 10 power plus 3. So minus 7 plus 3 is minus 4, agree? Minus 4. So now power of 10 is minus 4. And finally I can write 8 into 10 power minus 3 meter. Okay, 8 into 10 power minus 3 meter. So this is the answer required for the 8th question. Okay, so that is the second part, 8th bright fringe. First question is second part, 8th bright fringe distance is 8 into 10 power minus 3 meter. So in this problem they can ask fringe width also. So very simple, fringe width. Fringe width formula is beta equal to lambda d by d. Okay, they may ask fringe width. If fringe width is asked, fringe width beta equal to lambda d by d. Okay, so lambda d by d, lambda value 5 into 10 power minus 7. Okay, then d value 1.2 divided by small d value, that is 0.6 into 10 power minus 3. Okay, so that is equal to 5, and 1.2 by 0.6 is 2. Okay, 2 into 5 or 5, let it be like that only. Okay, so 1.2 by 0.6 is 1.2 by 0.6 is 2 it is. Okay, into 10 power minus 4. So 5 into 2, or directly use calculator. 5 multiplied by 1.2, it gives you 6 by 0.6. 6 by 0.6 you will get directly 10. Okay, so 10 into 10 power minus 4 meter, or you can write 1 millimeter. See, 10 power minus 4, 10 means 10 power 1. So 10 power minus 3 it is. 10 power minus 3 meter. So this is the fringe width in the question. It's not asked, but if it asked, then you must be knowing fringe width beta equal to lambda into capital D divided by small d. Capital D is the distance of the screen from the plane of slits. Small d is small distance, that is separation between the two slits. One slit, another slit. S1, S2 separated by distance of order of millimeter. So that's the question may be asked. So here they asked only 5th dark fringe and 8th bright fringe. So I have solved here. That's all about the first problem. So important problem this one. They may give reverse also. Any particular dark fringe or bright fringe they may give from center maximum. You are asked to find out the wavelength or any other data. So that's all about the first question. I will go to the second question. Just read the second question. So that is, in Young's double slit experiment, the slits are separated by 2.8 millimeter. Okay, the screen is placed 1.4 meter away. Determine the wavelength of the light used in the if the distance between the central bright fringe and the fourth bright fringe is 1.2 mm. Also find the distance of seventh dark fringe from central fringe, bright fringe. So firstly we have to find out wavelength of the light. The question is just reverse compared to first problem. So here in the second problem they have given slit separation. Okay, so the problem number 2, slit separation. So the habit is write the given data while solving the problem. Slit separation 2.8 mm. So we have to write this 2.8 mm in SI units. That is 2.8 into 10 power minus 3 meter. So first write neatly the given data in SI unit. So then the screen is placed 1.4 meter away. That is the distance of screen. Okay, distance of screen, capital D, equal to 1.2 meter. Then determine the wavelength of light used. We have to find out the wavelength lambda, question mark, lambda equal to how much. Then distance of the central bright fringe from the fourth bright fringe, that means x4. x4 is given, that is 1.2 millimeter. 1.2 millimeter. x4. X stands for distance of nth bright fringe from the central maximum or nth dark fringe. Here bright fringe will take. Now formula. Generally distance of nth bright fringe. Distance of nth bright fringe from central maximum. Bright fringe from central maximum. Central bright fringe only, right? Central bright fringe or central maximum. Okay, so the formula is xn is n lambda d divided by small d. xn is n lambda d by d is the formula, where capital D is distance of screen, small d is distance between the slits or slit separation. Now here n value is 4, fourth bright fringe. N equal to 4 for fourth bright fringe. Fourth bright fringe. Dark fringe means you have to take n value 1 less, I said in the previous problem. Now n value 4. Then given x4. x4 1.2 millimeter is there. So 1.2 into 10 power minus 3. 1.2 into 1.2 millimeter is 1.2 into 10 power minus 3 meter. Substitute. So xn, so 1.2 into 10 power minus 3, okay, equal to n 4 it is into lambda d by d. Lambda we have to find out, so that means which is unknown, not given, we have to find out in the question. Then capital D value 1.2 meter, so 1.2 divided by small d, slit separation, small d, 2.8, okay, 2.8 into 10 power minus 3. 2.8 into 10 power minus 3. Now to get lambda, we have to shift everything to other side. So bringing the, so otherwise you can cancel here. 1.2 and this 1.2 cancel. This LHS and RHS, 1.2 is there in the numerator. We can cancel straight away. So what is remaining? Now we have to bring this point in, or you can cancel also. This 4 ones are 0.7 times. I did reverse actually. 4 ones are 2.8. If you are not understanding, I rewrite. Bring the 2.8 this side. It goes to the numerator. 10 power minus 3 is there. Okay. Then already one more 10 power minus 3 in the LHS. 10 power minus 3 is there. One more 10 power minus 3 comes. So 2 10 power minus 3s. And bring 4 to the LHS. So numerator it is. So it comes to denominator. That is equal to lambda left out in the RHS. Therefore, wavelength of light, wavelength required in the question, wavelength of light lambda equal to 2.8 by 4, that is 0.7, 0.7, 10 power minus 6 meter. Okay, 0.7 into 10 power minus 6 meter. That's about the answer. We can write in nanometer. Nano is 10 power minus 9. If I write 10 power minus 9 here, I can multiply here 1000. Okay, so 700 into 10 power minus 9 meter, or you can write 700 nanometer, or 7,000 angstrom. Okay, 700 nanometer is same as 7,000 angstrom. If the question is find the wavelength in angstrom or nanometer, you have to express. Otherwise, you just leave the answer whatever you get and put the unit meter. SI unit it is. Next, last part of the problem here in this, also find the distance of 7th dark fringe. So distance of nth dark fringe. Nth dark fringe question. Nth dark fringe is xn equal to n plus half lambda d by d. Okay, n plus half lambda d by d. So that is the question. So now I write distance of 7th dark fringe. Okay, so continuation I do in the right side. Okay, so that is required is 7th dark fringe. Nth dark fringe is like this. Distance of 7th dark fringe. 7th dark fringe. Okay, so that is x7 equal to 7th dark fringe. What you have to do is n value you have to take 6. N value must be taken 6 in the formula. N is 6 plus half. Then lambda we got already. Whichever the number we got, same thing I substitute. 0.7 into 10 power minus 6. Okay, then into capital D value in the question. Capital D value 1.2 meter. Distance of screen is 1.2. Then divided by small d value. Small d value is given in the question 2.8 millimeter. So 2.8 into 10 power minus 3. 2.8 into 10 power minus 3. So now this number is 6 plus half is 6.5. 6 plus half is 6.5. Then calculation again 0.7 is there. 0.7 into 1.2. Okay, divided by 2.8 into 10 power, finally how much it is? 10 power minus 6 in the numerator. Wavelength we got here 10 power minus 6, and in the denominator we have 10 power minus 3. So this is minus 6 plus 3, so 10 power minus 3, and ultimately the number is, what you can do, 6.5. Use calculator. I am doing the calculation in calculator. Into 0.7 into 1.2 divided by 2.8. What you get is 1.95. So the number is 1.95 into 10 power minus 3. Okay, meter. So this is the number 1.95 into 10 power minus 3 meter. Just substitution in calculation. We can also write it as 1.95 millimeter. 1.95 millimeter. This is the answer. Okay. So that's all about the second question. Distance of 7th dark fringe. N plus half of lambda into d divided by small d. That's all. Then next question, last question. Okay. So I'll rub this. I'll go to the next question. I hope you understood this problem. Reverse it is given. That is bright fringe. Nth bright fringe distance is n beta also you can take. Xn is n lambda d by d, or you can also take n into beta, because lambda into capital T by small d is beta. That way also you can get fringe width, you can get here directly. Then you can calculate wavelength. That way also you can solve this question. And the last question, in Young's diversity experiment, screen is placed at certain distance. Okay. Now first situation. Now what happens? When the screen is moved away 10 cm, fringe width increases by this number. Calculate the wavelength of the light used. Okay. When the slit separation is 1 mm. So this is something tricky question, but not very lengthy question. So first situation, the question number 3. So first, initially I write beta equal to lambda d by d. Okay, certain separation between the slits, certain separation between the slits and the screen. So this is the capital D now, and the fringe width is beta for this situation. Now later what happened? The screen is moved away. Okay, this is the position of the screen. Okay, so this is the position of the screen. So then it is D dash. D dash equal to D plus 10 centimeter moved away now. So screen comes to this position. This is the initial position. Later it comes to here. Screen position. New position is dashed line. This one. So D plus 10 centimeter or 0.1, because 0.1 10 centimeter is equal to 0.1 meter. Correct. So this is the first case. Now later what happens when the screen is moved? When screen is moved away, screen is moved away by 10 centimeter, that is 0.1 meter. Fringe width, this is the fringe width initially fringe width I write, fringe width beta, later fringe width, new fringe width beta dash, new fringe width beta dash equal to lambda into, now what is capital D? Screen is moved away means capital D change into D dash. Okay, D dash divided by small d. Okay, so then what happens, you see the D dash you have to substitute. So that is beta dash equal to lambda into, what happens, capital D is D plus 0.1. Okay, D plus 10 centimeter actually. This 10 centimeter can be written as 10 centimeter change in the position of the screen, that is 10 centimeter. 10 centimeter in meter, 0.1 meter. 10 centimeter equal to 0.1 meter. That's what I wrote here. So then divided by small d as it is. Okay. Now splitting this beta dash, lambda d by d. Okay. Plus lambda into 0.1. Just split lambda into d by d one term. Lambda into 0.1 by d. Okay. That's it. Now, but we have lambda d by d is beta. Yes. So beta dash equal to beta plus lambda into 0.1 divided by small d. Now what happened in the situation? The fringe width increases by this much. Original fringe width beta, new fringe width is beta dash. Increases means what? Fringe width increases means given beta dash. Okay, so I write beta to the LHS, bring minus beta dash minus beta equal to this number, lambda into 0.1 divided by small d. Okay, but given beta dash minus beta equal to how much? This number. Fringe width increases means initial fringe width beta, final fringe width beta dash. So beta dash minus beta, final value minus initial value is change in the fringe width. Change in the fringe width, beta dash minus beta is this number, that is 6 into 10 power minus 5. Okay, now equate this. Beta dash minus beta is this number given in the question, that is delta beta also I can write. Okay, this is equal to delta beta, change in fringe width. Increase or decrease? Here increase. When the screen is moved away, fringe width increases, fringes become broader. So fringe width, the separation between the fringes increases. When the screen is brought towards the slits, beta decreases, fringe width decreases. Okay, so now this substitution, okay, lambda into 0.1 divided by small d. Then I want the value of lambda. Small d is given in the question 1 millimeter. Small d is 1 millimeter. Rewrite. So this simplification, 6 into 10 power minus 5. Okay, equal to lambda into 0.1 divided by 1 millimeter is 10 power minus 3 meter. 1 into 10 power minus 3. So bring everything to the LHS. So that is the last part. 6 into 10 power minus 5 into 10 power minus 3. This denominator take into numerator LHS. Then divided by 0.1. Okay, equal to lambda. So this implies lambda equal to, last step, lambda equal to, see simplification, 6 by 0.1. is 60. Multiply 10 here, 10 here. 0.1 into 10 is 1. So 60